You know, when you think about a pharmacy, you probably picture a pharmacist behind a counter. But today's most advanced pharmacies, they look more like high-tech factories, with robots doing a lot of the work. But even with all that automation, there's a hidden problem slowing things down. Today, we're going to look at some research that found a really clever way to organize these robotic pharmacies to make them way faster and more efficient. So this right here is an automated drug dispensing system. You've got a robotic arm that just zips along a track, grabbing medications. It looks super fast, right? But here's the thing. The biggest delay isn't actually the robot's speed. It's the travel time. All those wasted moments as the arm has to go from one end of the machine all the way to the other just to fill a single prescription. Okay, so here's where we're headed. We'll start by digging into that pharmacy bottleneck. Then we'll unpack a really smart two-step strategy that involves scattering and then clustering. After that, we'll look at the efficiency payoff. Did it work? And finally, we'll talk about what this all means for the future of humans and robots working together. So what is the real problem here? Well, in any warehouse, whether it's for an online store or a pharmacy, travel time is the #1 enemy of speed. A robot arm can be incredibly quick, but if it has to travel long distances between each item it picks up, the whole system just grinds to a halt. The problem isn't the robot, it's the organization. You know, this challenge actually has a name in the world of logistics. It's called the Storage Location Assignment Problem, or SLAP for short. It's a classic puzzle that asks a really simple but really important question. Where is the absolute best place to put every single item to make the whole system run as fast as humanly or robotically possible? Now, the old school solutions to this were pretty basic. You either stored drugs alphabetically, or you put the most popular ones in the spots that were easiest to reach. But these methods have a huge blind spot. They totally ignore the relationships between the drugs. I mean, if two medicines are almost always prescribed together, why on earth would you store them next to each other? The traditional methods just didn't think that way. And this is where a much smarter approach comes into play. Researchers developed a whole new strategy to tackle this exact problem, one that actually considers all the factors that the older methods were missing. They call it the Scattered Storage and Clustered Allocation Strategy, or SCCA, and the name itself is a pretty big clue to its powerful two-part logic. It combines one idea that sounds totally counterintuitive with another that is just perfectly logical. So the strategy unfolds in two main stages. First, you have to scatter the drugs, and second, you cluster them. Yeah, I know, scatter and cluster sounds like a complete contradiction, but trust me, let's break down how these two steps actually come together to create a brilliantly organized system. All right, first up, scattering. Now this is going to sound a little weird. Instead of keeping all of one type of drug in a single bin, this strategy does the exact opposite. It intentionally spreads out multiple bins of the very same drug across different machines. It seems strange, I get it, but there's a genius reason behind it. Here's the logic. Scattering creates flexibility. See, with copies of a popular drug available in multiple machines, it's suddenly way easier to group all the different items for one prescription within a single robot's reach. You're no longer stuck sending a robot to machine 1 for drug A and then all the way over to machine 5 for drug B. Scattering lets you create these perfect little prescription kits inside each machine. So, once the drugs are all smartly distributed, it's time for step 2, clustering. And this is where the magic happens inside each machine to make the robot's job incredibly simple and fast. The researchers used a really smart algorithm that basically works like this. First, it looks at the most popular drug in a machine. Then, it crunches all the prescription data to find its most common partner drug. And boom, it places those two right next to each other. It keeps building these little partnerships and groups, and then, and this part is key, it gives the most popular clusters the best real estate, the spots closest to the pharmacist. It just repeats this process over and over until every single drug has an optimized home. So the million-dollar question. After all this clever reorganizing, does it actually work? Does all this scattering and clustering really speed up the pharmacy? And the answer from the research is a huge, resounding yes. The strategy doesn't just work a little bit. It significantly improves efficiency. By totally reorganizing the pharmacy's brain, the robot's physical movements become shorter and faster, and that saves precious time on every single order. So the real insight here is that organizing a warehouse isn't just about how popular an item is. It's about understanding that hidden network of relationships between all the items. This strategy is a winner because it does both. It still prioritizes the popular drugs, but it also makes sure to keep their related buddies right by their side. And you know, this whole thing is about so much more than just filling prescriptions faster. This research really points to a bigger shift in how we think about automation. It's not just about building faster robots anymore. It's about building smarter systems for those robots to work in. And that really gets to the heart of it. The study drives home the point that these are human-robot cooperation systems. I mean, optimizing the robot is great, but that's just one piece of a puzzle that ends with a human pharmacist. Real, true efficiency comes from making the entire system flow seamlessly, from the robot's first move all the way to the pharmacist's final check. And this leaves us with a pretty fascinating final thought. We've seen how finding the hidden connections between medicines can completely transform a pharmacy. So what happens when we apply that same logic to other things, like groceries in a warehouse, or tools on a factory floor, or even data on a server? The next big leap in efficiency might not come from a faster machine, but from a deeper understanding of the hidden relationships that are all around us.